Hello. So what we're going to be doing today is I'm going to show you how to graphically solve a problem. And so as we graphically solve the problem, then maybe you'll see sort of how this works. You can also solve problems analytically, but I want to show you how to do it graphically because this was the old way of doing it. And it still works, and sometimes it's very useful to do this. And so to do that, to solve graphically a problem, you're going to need graph paper. Now, if you don't have graph paper at home, you can print graph paper out online. So what I did was I just Googled free graph paper, and one of the first sites that came up had this. It's not very good graph paper. It will serve for what we want to do. There's all different sites out there. We can get all different kinds of graph paper that do all kinds of cool stuff. You're also going to need something to write with, and then you're going to need a protractor, and you're going to need a ruler. And really, if you're going into science or engineering, particularly the physical sciences or any kind of engineering, graph paper and ruler, graphing is actually good for you. A protractor and a ruler are going to be very useful to do like freehand things. It really, the way I've been solving problems, I've just been freehanding drawing. You really are better off doing what I'm about to do rather than freehanding. Okay. So let's start off saying that we have an airplane, and the airplane is flying in a particular direction. Okay, so we'll say that the airplane is flying to the northeast at 75 miles per hour. Okay, so airplane flying 75 miles per hour to the northeast. Okay, and so that's going to be my vector A. And then what I want to do is I want to have a stiff wind the aircraft is flying in. So what's happening is the aircraft is moving through the air, hence an aircraft, and the air is moving. And so the combined motion of the air plus the aircraft is the total motion of what this thing is doing. And so let's say that it's a stiff wind 25 miles per hour towards the north. And so we have 25 miles per hour towards the north. Okay, and so the combined motion of the two is going to be that. Okay, and so that is what I'm trying to solve for. Okay, so the way I'm going to do this is I'm going to do this graphically. So I'm going to start off with my graph paper, and what I'm going to do is I am going to take the graph paper and I am going to, first of all, mark the axes on the graph paper. And so take time to do it properly. Okay. So I'm going to mark the axes for my graph paper. Okay. So I marked the axes. Okay. And the first vector is 75 miles per hour to the northeast. Well, how do I do 75 miles per hour to the northeast? Well, what I'm going to do is I'm going to make a scale. And my scale is for every 3 centimeters, that's going to be 25 miles per hour. Okay. So that would work. Except that's a little bit awkward. So maybe what I want to do is say I want to make every centimeter 5 miles per hour. Okay. So, well, that's going to be too long. If every centimeter is 5 miles per hour, I'm going to have a vector that's going to be very long. It's not going to fit on here. So I need to think about this again and say, well, how do I want to make this vector so that it fits on my page? And again, I'm back to maybe 3 centimeters equals 3 centimeters equals 25 miles per hour. So I write my scale on here. So I write my scale, 3 centimeters equals 25 miles per hour. Okay. And then, so 75 miles per hour is going to be 9 centimeters. Okay, so what I do is it's to the northeast, so rather than just drawing generically to the northeast, I use the protractor, and I take the protractor, and what I do is I mark here 45 degrees. Okay, and so I mark on here 45 degrees. So I'm going to lay this down and mark 45 degrees to make this as accurate as possible. Then I'm going to use the ruler, okay, and I'm going to draw it in that direction, and so this is going to be 9 centimeters. Okay, so there is 9 centimeters. Now, that's going to be my first vector. That's the 75 miles per hour to the northeast. So then what I'm going to do is I'm going to say 25 miles per hour north. Well, 25 miles per hour is 3 centimeters. So what I do is where that ends up, I'm going to go straight north here for 3 centimeters. Okay, and I'm going to make sure it's exactly straight north for 3 centimeters. Okay, so I'm gonna from that one point, I'm going to go 3 centimeters straight north right there. Okay, now, so that's what it is to scale. Then I'm going to draw a line from the very beginning to the very end. Okay, so this was my vector A. This was vector A, that was vector B, and I wanted to draw this line right there. That goes from the very beginning to the very end. And so now what I want to do is I want to measure that. And so use the ruler. Okay. And so I measure it, and that is 11.2 centimeters. So that's 11.2 centimeters. And I can measure the angle as well. And so to measure the angle, use the protractor. And again, I put the protractor on there, and I measure the angle, and the angle is 52.5 degrees. So it's 52.5 degrees from the x-axis. Okay, and so now what I do is I say, well, 11.2 centimeters, 3 centimeters is 25 miles per hour. So if I divide 11.2 by 3, that tells me how many 25 mile per hour units I have. So 11.2 divided by 25, that is 0.448. Okay. No, sorry. Did that wrong. 11.2 divided by 3. Okay, so 11.2 divided by 3. Okay, so that's 3.73 times 25. Okay, so that is going to be 93.3 miles per hour. Okay, and at an angle of about 50, and let me make sure I actually measured that right. Okay, and so that comes out to be, well, actually, I think I think it's about 55 degrees. So it's about 55 degrees. So it's about 55 degrees. Okay, I had my protractor a little bit squirrely. So about 55 degrees, and at 93 miles per hour. Okay, now, that's the problem there. Now, if you do this analytically, what do you come up with? So we got 93 miles per hour at an angle of 55 degrees. If I do this analytically, find the x components here. So we had 75 miles per hour at a 45 degree angle. Okay, so 75 miles per hour at a 45 degree angle. So 75 miles per hour at 45 degrees, okay? And so if you figure out the components of that, then that's going to be 53 miles per hour I plus 53 miles per hour J. So then what we do is we add to that 25 miles per hour J, because that was what we were doing with the wind, and that comes out to be 53 miles per hour I plus 78 miles per hour J. Okay. Well, now we use Pythagorean theorem. That comes out to be 94 miles per hour. Well, graphically, we have 93 miles per hour. It's not bad. Okay. If we do this analytically, then what we comes up with is we come up with 56 degrees from the x-axis, or it's going to be 34 degrees from the y-axis. So again, that's pretty close to what we had here. You know, we had 93 miles per hour at 55 degrees. Mathematically, with the calculator, it's going to come up to 94 miles per hour at 56 degrees. So which one's right? Well, they're both within rounding error, so they both give the same results. And so these are equivalent ways of getting it. Now, what is the advantage of doing it graphically? Because this obviously took longer to do than punching a button to the calculator. Well, sometimes it's nice to be able to see it. If you are, for example, again, going into engineering and trying to produce a report or something, you want to draw things to scale so that your customer knows exactly what things look like. When you're solving a problem, it's useful to draw it pretty close to scale so that you can glance at it and mentally see, does the math look like it's agreeing with the picture? If it doesn't, something's wrong. Okay, either the picture's wrong or the math is wrong. Okay, and so if you just freehand it like I typically do, then the picture could easily be wrong. Doing it like this, the picture's not wrong. And so if they don't agree, you have a check to see if you got it right or not. And so that's kind of one of the advantages of this. It's a good skill, particularly because you're going to eventually have to be producing reports. Whether you're going into science or going into engineering, you have to produce reports. You want them to be accurate. If you have anything that's physical and you want to draw the thing, you want to draw it accurately. And so that's why this is a useful skill. Now, a couple of hints. If you're trying to solve a problem this way. And some people actually find solving a problem this way in a test is even easier than solving a problem using analytically, because you just draw the whole thing out, and because you can do this with as many vectors as you want to do. Now, to do it correctly, you want to draw it as big as possible on the piece of paper, because if you draw it in a little corner down here, a small error in your measurement is going to be a huge percentage. And so you don't want that. You want to make the percentage very small. So what you would do is you draw this as big as possible. All right, so this is how you graphically solve a vector problem.